I'll hand out your exams at the end of class. Does anyone have any questions over the homework? Any particular part or all of it? All of it? Okay, so we're given the function sine 2x on the interval from 0 to 3 pi over 4. Part B says approximate the net area bound by the function and the x-axis on the interval using left, right, and midpoint Riemann sums with n equal to 4. So remember, the n corresponds to what?
Rectangles within the area you're trying to do, right?
What'd you say, the rectangles? Yeah, so n is corresponding to the number of rectangles we're using to approximate the area. So it says we're going to take this function, whichever one it is, A, B, C, or D, fill that region up with 4 rectangles, and then use that to approximate the area. Okay. So you could either draw out the graph and split it into 4 equal pieces, or we could just use the formulas from 5.1. Again, something like this isn't going to be on the exam. It's sort of tedious computations, because we have to look at the left, the right, and the midpoint Riemann sums with n equals to 4. So if we remind ourselves here that our Riemann sum sum from k equals 1 to n of f evaluated at x star sub k times delta x.
So are we going to be asked to either review the left, right, or right?
No, just the definition. We saw the last 2 examples in 5.2. So this, depending on which Riemann sum we use, x star sub k varies. And for the right Riemann sum, I'll abbreviate Riemann sum. The right Riemann sum for x star sub k is actually what we use in the definition to evaluate the definite integral. The last 2 examples from 5.2, we did 2 examples like that. But the x star sub k, if we're using right Riemann sums, okay, I guess we're using this 10, is a plus k times delta x. I'll try this again. For the left Riemann sum, x star is a plus the quantity k minus 1 times delta x. And for the midpoint Riemann sum, the x star sub k is a plus the quantity k minus 1/2 times delta x. So since we're using only 4 subintervals, I think it's easier just to either look at the graph and break that up into 4 equal pieces, stopping at 3 pi over 4, or just to use, to look at the grid points. Remember the grid points were the endpoints of each rectangle? So like if I have, a region like this, with this particular rectangle here, the grid points give me the sort of the left and the right boundary of each rectangle. And this is really stuff from 5.1, which granted we didn't talk about directly in class. All right, I guess that'll stay there. It's really weird. The grid points were the x sub k's. So the x stars were were each location in some grid. So like, whatever value of x we choose to evaluate the rectangle's height at, that's where our x stars come from. And the x stars are x values in each subinterval that determine the height of the rectangle. But the grid points are defined as a plus k times delta x for k equals 0, 1, 2, all the way to n. Now our n is 4, so we're stopping at 4. Yeah, grid points start at 0. So let's look at what our grid points are. We need to know A, which is the endpoint of the interval given to us here from 0 to 3 pi over 4. 0 is our A, 3 pi over 4 is our B. And we need to find delta x. So I guess really this is what we're starting with. Step 1, we're finding the grid points, because the grid points enable us to use midpoint, left, and right Riemann sums. We just have to kind of shift them around for the x stars. So our delta x, in general, delta x is defined as b minus a over n. And so for us, that's 3 pi over 4 minus 0 divided by 4. Is everybody all right with that? So then delta x gives us what, or our delta x is what? Yeah. So our delta x for this particular example is 3 pi over 16. We might just look at one of these. It takes a while to do these. I don't know why this thing is just hanging out on the board.
Right over it with white.
Yeah. I don't think. Yeah. Well, then it appears behind it or in front of it. Yeah. So weird. All right. Whatever. Okay, so let's find our grid points. We have x sub k, and the k is what varies here. A plus k times delta x, which we just found to be 3 pi over 16. So all of our grid points are defined by 3 pi over 16 times k. In other words, the endpoint of all 4 rectangles will be defined once we go from 0, k being 0, 1, 2, 3, and then 4. So let me write this here just to kind of see where our input is. This k is what's varying. So we're going to find when k is 0, that means we're finding x sub 0, defined by 3 pi over 16 times k, which is 0. So our first grid point is 0. That means the left-hand side of the first rectangle starts at 0. Then k equals 1. So x sub 1 is 3 pi over 16 times 1, or 3 pi over 16. Then k is equal to 2. So the third grid point, x sub 2, 3 pi over 16 times 2, which gives us 3 pi over 8, or if you will, 6 pi over 16. 2 more to find. Find x sub 3. Is 3 pi over 16 times 3. That gives us 9 pi over 16. And then finally, x sub 4, 3 pi over 16 times 4. What was that? 3 pi over 4. Okay, so notice we start at 0, and then we end at 3 pi over 4. X sub 0 is A, x sub n is RB. And that's how it should work out, right? If our function's defined on this particular interval, we shouldn't have rectangles exceeding that left endpoint, which was 3 pi over 4. So then we can actually list the grid points out. So our grid points the first partition goes from 0 to 3 pi over 16. The next one, or the next rectangle, envision these grid points, these intervals that we're listing, as just the length of each base on the x-axis of each rectangle. Then the next rectangle starts at 3 pi over 16, and then goes to 3 pi over 8.
Would you just be able to add the base to each one to find the grid point?
To each, what do you mean by each one?
Like, so if you find the first one, and you're multiplying, no, maybe I'm thinking of something different. Because isn't the base the same in each one?
Yeah, the delta x is the same for each
Yeah.
one.
And then each one is half of that?
Not necessarily.
What do you just add on?
No, because, so I'm not quite sure I understand. I mean, so like if we have this region here, let's say, and we put in 4 rectangles, the 1, 2, 3, 4, let me scoot this over, drew too many. So the length of each rectangle is the same. That's delta x. That's 3 pi over 16. This length is 3 pi over 16, this one and this one. What we're finding is this location, this location, this location, and this location, and the ending. So that's what we're finding. Did that help?
Yeah, that makes sense, but I'm just saying, like, if the delta x is the same on each rectangle, wouldn't you just be able to find the first length and then add that to the next one?
Oh, right, yeah. If we know we're starting at 0, then we have 0 plus 3 pi over 16, plus another 3 pi over 16, plus, yeah.
Would that be like a shortcut? And
Yeah.
then you just seems like a lot of work.
Yeah, I mean, it is. But yeah, you can totally just add delta x because they're the same through each rectangle. So we have 0 plus 3 pi over 16, 3 3 pi over 16 plus another 3 pi over 16, and so forth. Third rectangle or the third grid point starts at 3 pi over 8 and then goes to 9 pi over 16. And then the last rectangle starts at 9 pi over 16 and goes to 3 pi over 4. So we use these grid points for all Riemann, left, right, and midpoint Riemann sums. With the left and the right Riemann sums, what we're plugging into a function is explicitly listed here as either the right or the left endpoint of each one of those subintervals. And then if we have to look at the midpoint, then we just take the point that's halfway in between 0 and 3 pi over 16. The point that's halfway in between 3 pi over 16 and 3 pi over 8, etc. That would give us our midpoint that we plug into the function. So then, I guess step 2 is to start evaluating left, right, midpoint Riemann sums. Let's just do the right Riemann sum. As defined above, we go from k equals 1 to n. Our n is still 4. The sum of f of x star, which is a plus k delta x for our right Riemann sum, as we defined that above as well, times delta x. And we know this delta x to be 3 pi over 16. And so listing out the grid points, we have all of our x stars. Or this a plus k delta x for the right Riemann sum. They're all listed here as the right, since we're using the right Riemann sum, they're the right endpoints. So 3 pi over 16, 3 pi over 8, 9 pi over 16, and 3 pi over 4. So the area is approximately, notice here delta x is always 3 pi over 16. So we can effectively take the 3 pi over 16 out of the sum and then just sum up the function values. Might not be enough room. And just sum up the function values here at the right endpoint. So we have f of 3 pi over 16 plus f of 3 pi over 8 plus f of 9 pi over 16 plus f of 3 pi over 4. So that's what our Riemann sum that we wrote up here, that's what that turns into once we evaluate that at the right endpoints. Does that make sense? So a lot of the notation is very heavy, but again, all we're doing is we're saying take this region, divide it into 4 rectangles, find the area of each rectangle. So this delta x 3 pi over 16 times f of 3 pi over 16, that's the area of the first rectangle. This times this is the area of the second, this is the area of the third, and this times this is the area of the fourth, and we're adding all of that together. Okay, so really that's 3 pi over 16. Our function was the sine of 2x, so this is the sine of 2 times that quantity. Plus f of 3 pi over 8 is the sine of 2 times that quantity, etc. that's what we're actually going to put into our calculator to determine the area. And that's going to give us an approximation to the area. So whatever that value comes out to be, that's going to be the approximation of the area under the function sine 2x using right Riemann sums. And since we have this thing right here, the only thing that would change, let me just copy that, because the only thing that changes when we do the left and the midpoint is what actually gets plugged into the function. That's the only thing that's going to change for the other Riemann sums.
So after you find the grid points, it's pretty much just plugging in the correct grid point into
Yep.
the original function.
Right. I don't know, maybe this is part 3, I guess. Left Riemann sum. All we're plugging into the function are the left endpoints. Plugging in these. So that's the same thing. Just different places of evaluation to determine the height of the rectangles.
So the fact that it's like I think it's like plus k minus 1 or something, doesn't really matter.
The fact that it's,
Like that star, that x star sub k equals a different thing than the right.
yeah.
Does it not matter? I guess I don't know what, I don't know.
As far as the approximate area, it does matter because you'll get a different area. If it's like, if it's an increasing function, is that what you're asking? Does it matter which ones we use?
I'll just talk to you after class, because I think I'm making it more difficult than it needs to be.
Okay. But yeah, it does matter. You'll get slightly different areas. The more and more rectangles we put in there, the better and better those approximations will be. So the closer and closer the left, right, and midpoint will be. But since we're only using 4, the left Riemann sum and the right Riemann sum and the midpoint, they would probably be off by a noticeable amount. Okay, so then the midpoint, like we said, the midpoint, we're just going to take half of 3 pi over 16 minus 0, and then that's our midpoint Riemann sum. Half of 3 pi over 8 minus 3 pi over 16, that's our midpoint. Half of this is our midpoint, and those are the values we plug in to the function for the midpoint Riemann sum. Okay, so questions on this? So like if we have this type of function here from 0 to whatever this value is, we'll call it b. And we say, let's divide this up into 4 pieces. And those are our partitions. We're making these, this is the length of rectangle 1 is here, so we have to say, all right, well, the first rectangle, do I want to use the left endpoint or that right endpoint to determine the height? So if I use the left endpoint to determine the function's height, it's 0. Then I go to my next rectangle and still use the left grid point to determine the height, and the height of my next rectangle is defined there. And then this rectangle, using the left endpoint to determine its height, it's defined there. So then we're saying, well, we've got this rectangle plus this rectangle plus this rectangle as the approximation of that area. If we say use the right endpoint in the first rectangle, then this is the right endpoint here, and the right endpoint here. So then we're finding all of this area. So depending on the function, one is an over approximation, the other is an under approximation. So typically the midpoint is essentially the average of the over approximation and the under approximation. So the midpoint is usually the best one to use for approximations. As we ended section 5.2, what we were looking at is we don't want an approximation anymore, we want an exact area. So whether we use left, right, or midpoint Riemann sums at that point, finding an exact area was really kind of pointless. Doesn't matter which one you use, they'll all three give you an exact area. Okay, does anyone have any other homework questions? So then let's start 5.3. Did anyone have any questions on those last two examples from 5.2? All right, here we're developing the shortcut method to find the net area. So just as a reminder, at the end of 5.2, we said we have to sum all of this stuff up, let n approach infinity, and we worked with that definition to find the exact area. So this is where we actually come up with a shortcut, I guess. Just like with derivatives, we had shortcuts. But the first thing we're going to look at is the area function. And so the area function is defined as capital A of x. And it says on the function f of t, between the function f of t and the t-axis, from a starting point of A to an ending value or point of x, if we take that net area that gets accumulated as x varies, then we're going to label that as the area function. So notice it is a function of x, and where that x is the kind of this upper limit right here. So this is where our input goes. Anything that gets plugged into the area function gets plugged in as a value of that upper limit, and only that upper limit. And so to make sense of that, here we have our function f of t, or at least to get a visual sense of that. F of t from some interval a to b, and we're saying that the area function stopping at x or at x is indicating the ending point of the accumulation of area. So as x varies from 1 to 3 to 5 to 100, then the ending point up here is stopping. It says what's the net area from A to 5 to 10 to 100. So as x varies, what it's doing is it's accumulating or accounting for all of this area to wherever we choose to stop. Does that make sense? So if I said what's the area function evaluated at 2, maybe it's this right here. We go from starting point A to an ending value of 2. This is the area function evaluated at 2. It gives us the net area underneath that function and the t-axis. Do y'all have any questions about that? And so we'll look at some examples just to kind of get used to that function. But looking at another example, maybe make sense of the area function. Here we've got the solid line is f of t, and then as x moves from a to wherever, what we're plotting here with this dashed line is the area function, or the amount of area accumulated. So notice if we start here at A, I guess that's as far as we can go back. Yeah. So if we start here, then the function's going to start out at 0. It's technically, I don't know if I can draw on this or not. If we start here at this line, and we say what's the area from here to here, and we're saying what's the area of that line. So the area is 0. So the area function starts out at 0. So think of the x, the t and the y-axis here. When we graph the area function, that's the area on the y-axis. The t-axis is still the t-axis. So the outputs that we plot, the inputs are still the same. The outputs are simply how much area has been accumulated. So if I go, oops, it's kind of laggy. So if I go over to this value, and I say, well, what is that area? I don't know, there's no specific values, but I know that I've accumulated some area. Maybe that area is 6. So the area function then has a point for that particular x value, or that t value rather. I don't know what it is. But that says that since my area is 6, I'm plotting the point x comma 6. And then I move some more and see how much area I have, and I plot that point. Okay, so the amount of area is the output here when we're graphing this dashed line. Okay, so underneath the function f of t, I start out with an area of 0, and if I start moving, increasing x, notice that all of this is above the axis. So all of this green stuff is above the x-axis. So the entire time my area function is increasing because I'm just gaining more and more area, right? Does everybody see that? So the area function keeps increasing because the green area is all above the x-axis, which means that it's all positive and I'm adding more and more area. So the area function is increasing, just means you're accumulating more area under the curve. And then I reach point C. What happens directly at point C with the area? But before it starts to decrease, at that location exactly when x is C, do we gain any area or lose any area? No, because there's nothing above or below the x-axis. The function is on the axis. So at x equals to C, there is no gain or loss of area, which is why we see this maximum here on the area function. In other words, if we thought about the rate of change of area, the slope of the line here, the tangent line at the area function is 0, right? It's a horizontal tangent line, or a 0 rate of change. We're not accumulating or losing any area there. But then immediately after this point, I don't know why it's being weird. Immediately after this point C, then now the area is below. So what we had accumulated, we start taking away from, which is why we see a decrease in the area function. So then we keep taking away and keep taking away, and that area decreases. If we had the same amount of area in green as we did in this orangish whatever color, then the area function would reach 0 again, or the t-axis. So if the area function were over here on this axis, then that means at that particular value we have the same amount of area above and below the x-axis. Maybe if we looked at like x squared or t squared. from 0 to 2. Maybe you can sort of envision what the area function would look like for this particular one. T values are the same. Output is the actual area. So if I start at 0 here, what's the area? 0, there is no area there. And then I'm going to vary x all the way to, I stop at 2, but we see that if I do that, I'm just accumulating area the entire time, right? So just keep gaining all of this area until I stop at 2. So the area function is, we're constantly gaining area. So that's what our area function would look like. This is the area function. We're saying, well, the area is definitely increasing at a constant rate. Does that make sense? Any questions on, hopefully help us understand that area function a little bit better. There are a lot of functions in math defined by with the integral involved. I think up to this point, this is probably the first function that we see defined in terms of an integral. So think about this as an accumulated area as we start at a and end at x. All right, so we're given this figure and two things. One, the area function evaluated at x, capital A of x, is the integral from -1 to x on this function here, f of t dt. So just, again, pay attention to the input. If I plug a value into the area function, that value goes here as the upper limit. That lower limit is already defined as -1, which doesn't change. Okay, so we're given that, and we're given another area function. Let's call it capital F of x, defined as the integral from 3 to x, f of t dt. So similar functions, they're still accumulated area functions. One starts at -1, the other one starts at 3. Okay, so we're given those two functions and the figure. Let's find capital A of 3. Each one of those tick marks is 1 unit. So what is capital A of 3 equal to? If I plug 3 into A, what does that function then look like? It's A of 3. So that says that's the integral from -1 to 3 on f of t dt. So what is the integral from -1 to 3 on that function?
27.
27? What do y'all think?
-27?
So yeah, is it 27 or is it -27? Okay. How would we know that it's negative? Right, since it's below the x-axis, it's a negative.
What if there was no picture? How would we know?
There was no picture, we couldn't evaluate this. You have to know what this function is, f of t, in order to be able to evaluate these things, which is why we're given the picture. What's capital A evaluated at 5?
Three.
Is what?
3.
Capital A of 5? So be mindful of where A starts.
Oh, yeah, we're not starting at 3, so then.
Negative 24.
So that means we're taking the integral from -1 to 5 on that function, f of t dt. So from -1 to 3 is -27, like we just found. And then we go from 3 to 5, we get an area of +3 because it's above the x-axis. So A evaluated at 5 is -24. Do you have any questions on that? What's capital F evaluated at 3?
Zero.
0, yeah, how do you know it's 0?
Because it's just 1 point.
Yeah. Remember, capital F starts at 3 to x. X here is 3. The property we looked at yesterday, if we say what's the net area from A to A on any function, it's always 0. Because if we look at the area from A to A, and we're just finding the area that's generated by a point. Right? If the point is on the x-axis, then there's no area there. Or if we thought about it, even if it wasn't, if we say, here's my function, I'm going to start at A. Maybe this point is up here, but then we're saying what's the area of that line? And lines have no area. Okay, last example here, what's capital F of 9?
-32.
So capital F is the integral from 3 to our stopping point 9 of f of t gt.
-32?
Yeah. Okay, yeah. So f starts at 3. If we go from 3 to 5, we accumulate a +3 area. And then if we go from 5 to 9, we have an area of 35 that's below the x-axis. So the net area from 3 to 9 is -32. Do you have any questions on that? So now we're going to look at kind of a similar thing given a particular function on an interval. So the function 2t plus 3 on the interval 2 to x. And the first thing we're going to find is the actual area function. So what is capital A of x for this particular information?
t squared plus 3t. Do you have to take like the integral of it?
Yeah, so we haven't actually connected, we're about to connect the antiderivative to the area. But right now, we don't know, the signs are similar, but we don't know right now, is area actually the antiderivative? We just want to fit it in with the definition of the function. So the area function says we take the integral from a to x. What's our a?
2.
2, because it's defined here on this closed interval 2 to x. 2 to x of f of t dt. F of t is given as 2t plus 3. So I think I've reserved space in this section to talk about the difference, but notice that there is a difference between saying, you know, what's the integral from 1 to 2 on x squared dx versus the antiderivative of x squared with respect to x, right? So even though those symbols look the same, once we put these numbers up here, it takes on a completely different context. Because here, without the numbers, this was our indefinite integral. And what that simply meant was find the antiderivative. And we know that the antiderivative is a function. Right? That was from 4.9. When we see something like the integral from 1 to 2 of x squared dx, what is that interpretation?
Just that part of the graph of x squared.
Yeah, so we look at a piece of x squared from 1 to 2, but when we evaluate this, what does it give us?
An area.
An area, what kind of area?
An area from 1 to 2.
Okay, close.
A net area?
Yeah, it's the net area. Here, it happens to be the area because the function's above the x-axis. But in general, these things give us a net area. We, of course, know the net area is just some number. So these things are called definite integrals. A definite integral is the net area. An indefinite integral is simply the antiderivative. One's a function, the other one spits out a number. So up to this point, we don't have any connection with the two. The only connection is that the symbol, the elongated s, is the same. Other than that, that's it. We have no way at this point to know that this area function here, defined from 2 to x on 2t plus 3, is any way related to an antiderivative whatsoever. Okay, then, second thing. Find or evaluate A of 5. So we're going to write out, in terms of the integral, what A of 5 is. A of 5 is the integral from 2 to 5 on 2t plus 3. Is everybody okay with that? So how do we find that?
Just took the stuff from 5.1 and 5.2 and put rectangles in it.
Okay, so no matter, but if we put 50, 100, 1,000, a million rectangles in there, that's a long and lengthy computation, right? and it still would not be exact. So this right here from 2 to 5 of this function says, give us the exact net area under this function in the t-axis from 2 to 5.
Can you make it equal to the
Equal to,
5
okay, so where would the 5 come from?
from the,
This one?
yeah, or would you make it equal to 3? So that's the difference between 2 and 5.
So we don't know, but this is our input, a of 5, and we're trying to find a of 5. A of 5 is some number. That number is the net area on this right here. So there's two ways to evaluate that, right? We can evaluate it using the definition of Riemann sums, the limit as n goes to infinity. Or we could say, well, let's just write out or draw out what we're looking at here. Okay, so I'm going from x value of 2 to 5, and I'm going to plot the function or t value from 2 to 5. And I'm going to plot the graph 2t plus 3. So this is y-intercept of 3 and a slope of 2. So there's 2t plus 3. Is there another way to find the area? From 2 to 5. So we're finding this area. We can do that the long way with the definition, the limit, all that stuff. Or we could just say, well, that's a pretty plain geometric figure. Do I know the area of that figure? Well, we did an example like this in class the other day. Area is half of the base. Oops. The area of that figure, half of the base times the sum of the parallel sides. So what's the length of the base? What's h? 3. What's the length of side A?
7.
7. We get that from plugging 2 into the function. So 2 evaluated at 2t plus 3 gives us 7. And the height of side B?
13.
13. 5 in for t, 2t plus 3. Just 13. So the area of that region that we need for a of 5 is 1/2 of h. So half of 3 times the sum of 7 plus 13. So we have half of 20 times 3, which is 30. So that means a of 5, the net area from 2 to 5 on 2t plus 3 in the t-axis is 30. We could evaluate that the long way, like we did at the end of 5.2, and come up with the same result. It's just that the process is a little bit more involved. So often it's helpful to think about what kind of, when you're given an integral like this, especially since we don't have any other techniques outside of geometry and the definition to evaluate. Okay, any questions on part 2? Okay, so here in part 3, let's do what we did similarly to part 2, but find a of x. So remember, we've already written down what a of x is in part 1. We said a of x was the integral from 2 to x on 2t plus 3 dt. So let's just do the same thing here. Let's draw this out from 2 to x. Graph 2t plus 3 again. There's our line, 2t plus 3. This time we're going to go from 2 to x though. So from 2 to x. So again, can we find this area? Well, what's the length of the base?
Delta x. 2 plus x.
Okay. Yeah. So, it is there is a change in x, but we can be very specific with that change. If x were 10, what's the change there from 2 to 10? Yeah. If I go from 2 to 10, I know that change is 8. It's 10 minus 2. Right minus left gives us that change. The length of the base of this particular figure is x minus 2. Again, it depends on where we stop, right? Just like we stopped at 5, what was the length? It was 5 minus 2. X minus 2 gave us the length of the base. This side length here is still 7 because that's just f of 2. What's the side length? What's the side length for the right side of that figure?
2x plus 3.
Right. Just plug this value, the stopping value x, into our line 2t plus 3. So that's just 2x plus 3. Everybody okay with that? So let's look at the area for that figure. It's going to be in terms of x because, you know, x is some unknown, but we can still construct the area for that. So the area, we're going to take 1/2 the base times the sum of the sides. Let's see what that is a little bit more neatly. So we've got 1/2 times x minus 2. And the green quantity now we have 2x plus 7 plus 3. So we have 2x plus 10. If I distribute the 1/2 into the 2x and plus 10, they're both divisible by 2. So I'll just have x minus 2 times x plus 5 with no 1/2. And let's just multiply that out. That's x squared plus 3x minus 10. So the area function stopping at x from 2 to x under 2t plus 3 is x squared plus 3x minus 10. Questions about that formulation? Yeah.
Wouldn't it be x minus 1 multiplied by x plus 5?
Oh, no, so the 1/2 got distributed into the 2x plus 10,
Okay, but not the x minus 2?
not the x minus
Okay.
2. No, like, you know, if we multiplied like 3 times 5 times 6, we wouldn't multiply 3 times 5
Oh,
times
okay.
3 times 6, right?
Yeah.
So let's check that. Our claim was that we started off with this area function, integral from 2 to x on 2t plus 3 dt, and we said that's equivalent to the function x squared plus 3x minus 10. Let's check our previous result and see if this matches with a of 5. The integral from 2 to 5 of 2t plus 3 dt, that in part 2 we got that to come out to be 30. Okay, here again, let me just emphasize this. A of 5 was this here, plugging in 5 for x. So we found in part 2 that was 30. Is 5 squared plus 15 minus 10 30? 25 plus 15 minus 10 is 30. So the x squared plus 3x minus 10 is just the formula for this area function on this particular instance. If I give you any stopping point, we could say what's the net area from 2 to that stopping point on this function, and always draw out that quadrilateral, find the area that way. Or instead, now we can say, well, if my stopping point's x, to find the area, all I have to do is square it, add 3 times it, and then subtract 10, and that will give me the same area every time. Any questions on that? So we would expect that even though it's 2t plus 3, we would expect this to be a function of x. This area is completely determined by where we stop, right? The function's set and the starting point is set. We would expect that to be a function of x because it depends on x. So I know it's close to break. We've got to let's just finish this because it's a very important connection that we're about to make. So in part 4, let's look at the derivative. So look at the derivative of the area function versus or compared to the integrand f of t was 2t plus 3. So we had the area function as x squared plus 3x minus 10 from the previous example. And our integrand, f of t, was 2t plus 3. Okay, so we want to look at the derivative of the area function. In other words, what is a prime of x, or the derivative with respect to x of the area function, equal to? 2x plus 3, right? Derivative of capital A, 2x plus 3. But notice the derivative of the area function is f evaluated at x, which is 2x plus 3, right? If f of t is 2t plus 3, f of x is 2x plus 3. So it turns out that it's not a coincidence that the derivative of the area is the original function we started with in terms of x. So let me make a note. Let's make a note of that because we see that here explicitly. It's an important one. The derivative of the area function here in this example is f of x, and where that lowercase f of x came from was this right here. This was our 2t plus 3 in this integral. This was our f of x, or sorry, our f of t. So basically the derivative of the area function gave us that function back, right? Just in terms of x. So maybe that's a good point to stop at. We'll continue with this, but maybe think about what this means in terms of what we're finding and what we finished in 4.9, right? So, and we'll take a break, but maybe just really try to think about what that implication is for us. Still have any questions before we go on break? Okay, so I just wrote down what we said for the last example, and I guess we should remind ourselves from the last example that it was just a linear function. So we're going to look at what this means for that example and then try to see if we can make it apply to other functions that are not linear. So what that means is that, I guess depending on the notation, you look at the derivative of capital A of x is the derivative of the integral definition of A of x. But we said that was the same thing as just f of x. So what does that give us? If I know the derivative of the area function is f of x, then what is the area function? We know the derivative of the area function is f of x. So let's look at it this way. What if I told you that the derivative of x squared is 2x? What do I know about x squared? I know something about the derivative of x squared. I just want to talk about x squared.
It's the antiderivative.
Yeah.
Integral of 2x.
Good. Right, so if I know the derivative of x squared is 2x, then the antiderivative, oh, let me write it the other way so we're not. Then I know x squared just by itself, then I know x squared is the antiderivative of 2x. Right, we know there's a difference of a constant here plus c. We'll just say that's 0 for right now, but if I know something about a derivative of a function, then I know something about the function. Namely, if I know the derivative of the function, I know the antiderivative. So what I write that? I'm going to erase this. If I know the derivative of the area function is lowercase f of x, then what do I know about the area function? Right, it's the antiderivative of f of x. So, there's some technicalities that we're not writing out, but that's the main idea. What we're looking at is, with this linear function, the area is an antiderivative. So from this point in this example on a linear function, we have now associated the antiderivative to the area, or to the net area. So let's write that out. That is the area, which is in general a net area, is, well, we'll say is an antiderivative of f of x. So now we want to say, well, is that just coincidental because we had a linear function? Or does that concept or that notion actually apply to any function we look at, whether it's linear or not? And actually, this part right here that we're looking at, again, what we're looking at there in red is saying the derivative of the area function is f of x. That's the first part of the fundamental theorem of calculus. So the derivative of the area function is f of x. And we'll come back to that. So this figure is what all we're going to use. It's not like rigorous or anything like that, but this figure is what we're using to determine or to answer the question: is the area function, which is our net area, is the net area an antiderivative? Antiderivative of f of x. For any f of x, not just a linear function like in that last example. I.e., for any continuous function on AB. So we're just going to look at it visually. and say, if I take the accumulated area all the way up to x plus h, that's going to be my capital A of x plus h. And so if I look at that, all of that area, and I break it into pieces, A of x, the area all the way up to x, and the area of this rectangle here from x to x plus h, we can write that out as such. The area, the accumulated area from starting point to x plus h is approximately this area, A of x, plus the area of this rectangle here. So if I find the area of A of x and the area of that rectangle, put those together, that's going to give me this area of A plus h. But the area of this rectangle here, notice the base goes from x to x plus h. So the base length of this rectangle is just h. And the height of that rectangle is evaluated here. So the height of that rectangle is evaluated or determined by f of t evaluated at x. In other words, the height of that rectangle is just f of x. So if we take those two things together, then we get this right here. And of course, how would we make that exact? The area up to x plus h would be exactly equal to that if we let what happen?
H approaches 0.
Right, good. As h approaches 0. So as h approaches 0, this x plus h simply becomes x, right? So if we let h get closer and closer to 0, then this ending boundary of that rectangle gets closer and closer over here until it's just that right there. Okay. So we're just going to rearrange this right quick, this approximation, and solve that approximation for f of x. So we're going to subtract a of x on both sides, and then divide through by that h. So we can see that f of x is approximately the area up to x plus h minus the area up to x divided by h. And then again, we say that becomes exact as h approaches 0. So if I take the limit as h approaches 0 on capital A of x plus h minus capital A of x all over h, that's exactly equal to the limit as h approaches 0 on f of x. So what is the limit as h approaches 0 on f of x, the right-hand side?
Isn't it just f of x?
Yeah, it's just f of x. Right, this function of x on the right-hand side does not involve h in any way. So that right-hand side is just f of x. This is just f of x. What is the limit as h approaches 0 on a of x plus h minus a of x all over h? I'll give you a hint. We saw that definition in chapter 3.
It's the derivative of f of x?
It's the derivative of, not f of x. It's the derivative of, you're on the right track. The derivative of f of x is defined as the limit as h approaches 0 on the difference quotient f of x plus h minus f of x all over h. I hope y'all vaguely remember that definition. So if that's lowercase f prime, then what is our left-hand side?
It's the integral.
The antiderivative of the area function?
Not the antiderivative,
The derivative.
the derivative, right? So this function, lowercase f, is totally arbitrary. I could say that the derivative of w with respect to x is w of x plus h minus w of x all over h, right? So since the function we're looking at is capital A, then this side is just capital A prime. Writing that in different notation, what we're seeing here is that the derivative of the area function is f of x. And I always said that f of x was a continuous function from a to b. So we can extend the idea of the derivative of the area being the function itself. The function that's in the integral. So that is, if we write this out according to the area function's definition, the derivative of the integral from a to x of f of t dt is equal to f of x. And like we said earlier, that's the fundamental theorem of calculus, part 1. So the order of operations here from left to right, we would say we've got some function f of t. If we integrate f of t and then take its derivative, what we end up with is the function in return. The same function that we started with a variable of x instead of a variable of t. So integrate it and then differentiate it, we arrive back to the same function. And we already knew that from 4.9, right? The derivative and the antiderivative are inverse operations. So are there any questions on that? Now, particularly what we have here is the connection between the area and an antiderivative. We'll see how to evaluate that in a minute, but this is telling us that the derivative of the area function is the function itself, and if we know something about the derivative, then what we know by implication is that the area function is the antiderivative of the function of x, or f of t dt, if you will. Doesn't matter. It's just the antiderivative is related to the area in a particular way. So I want to skip the next page and go to, I want to go to this page here, the part 1 of the fundamental theorem of calculus, because that's kind of where we ended. And it says if f is a continuous function on AB, then we have our area function defined. It's continuous and differentiable. And the area function satisfies that the derivative of the area is the function. That is, the derivative with it all written out. We've seen that a few times, which means the area function is an antiderivative of lowercase f. So we're going to use this fact, which is the first part of the fundamental theorem, to evaluate a couple of things, just so we can kind of get used to looking at that or working with that as well. So example 1, what's the derivative of the integral from 1 to x on sine squared t dt?
Just sine squared t.
Close.
Or t sine squared t.
Sine squared x.
Sine squared x. look what happens when we take the derivative of the integral up to x on this function of t. It just becomes a function of x. So this function of t now becomes this function of x. What's the derivative of the integral from 5 to x on the square root of t squared plus 1?
Square root of x squared plus 1.
Right, that's just the square root of x squared plus 1. That function of t just becomes a function of x. Once we look at the second part of the fundamental theorem, we'll look at this in another way, because then we'll have a means to actually evaluate this. But this is by far the shortest way to evaluate these kinds of things. All right, more generic ones that are, I would say, that are less common are like example 3 and 4. And notice we're not stopping at just x. We're stopping at, x cubed and x squared, for example. So really what we're not seeing in that definition is the chain rule. I mean, the chain rule is there in that definition when we take the derivative. It's just the derivative of x is 1. So we're not seeing that. So if I write this out, and then we'll write the more generic one out. So the derivative of the area function we said is just f of x. But again, what we're not seeing here, I'll highlight this x again. What we're not seeing is that it's multiplied also by the derivative of x. So we'll write this out in general. The derivative of the integral from a to some function, we'll call it g of x, on the function f of t dt is f of x, f of g of x times the derivative of g of x originally, like I said, when we presented that rule of the fundamental theorem of calculus part 1, we didn't see that part because the derivative of x was just 1. So we compose with the upper limit of integration with these. We compose the function of t with the upper limit of integration, and then multiply by the derivative of that upper limit. Does that make sense? Where that chain rule is kind of hiding. So the derivative of this was f of x times 1. So the derivative then of the integral from 1 to x cubed on cosine t squared dt, what would that be?
Wait, 3 cosine x squared?
Not quite. What we have to do is we have to take the x cubed, which is this g of x right here. We still plug it into the function, it's still f evaluated at that value, or that x cubed. But then we have to multiply also by the derivative of the g of x part.
So that would be cosine of x to the 6 times 3x squared.
Right. So we're going to plug in x cubed in for t and get cosine of, we're going to get the cosine of that thing squared, where we're plugging in x cubed. But then we have to multiply this by the derivative of x cubed. So we have 3x squared times cosine of the quantity x to the 6th power Any questions on that? All right, so like just point out here that with these first two examples, it's no different. We plugged x into the function of t, but what we didn't see is that we multiplied it by also the derivative of x, which of course is just 1. So it's still sine squared x. Plug x in for t and take the derivative of x. So that's why we're not seeing that stuff there. But that's what we did. Okay, then how about example 4?
Two over x to the seventh.
Okay. So we plug in x squared for t, and then multiply by the derivative of x squared. X squared in for t, and then multiplied by the derivative of x squared. So we have 2x divided by x squared to the 4th, x to the 8th, and 2x over x to the 8th is 2 over x to the 7th. Do y'all have any questions on that? All right, so I'm going to go back a page. So that was the first part of the fundamental theorem of calculus. Area is an antiderivative. We saw it's just a little more technical than that, but that's kind of the gist. So then how do we evaluate the definite integral from a to b of f of x dx? We have, from 5.2, we looked at a geometric method, which was limited, right? If we didn't have some nice geometric figure, it didn't work. What always would work was the definition, which was the limit as n approaches infinity on the Riemann sum. We looked at 2 of those examples. And then now we have a third method by the fundamental theorem of calculus part 1, where we said that area is an antiderivative of f of t, sorry, f of x. So if we take, let's just consider consider a continuous function. F of x on some interval, some closed interval a to b. Call the antiderivative capital F of x if we call the antiderivative capital F of x, that's just one antiderivative, right? Like if I say f of x is 2x, and and then I say capital F of x is x squared, that's just one particular antiderivative, right? I could say, well, I've got another antiderivative, call it capital A. Another antiderivative I could say is x squared plus 4. Both are antiderivatives of x squared. Do you all agree? Because if we take the derivative of either capital A or capital F, we get lowercase f. Everybody okay with that? So then what we're going to say is, if capital F of x is an antiderivative of lowercase f, then also capital A of x plus some constant is also an antiderivative of lowercase f. So then what we're looking at this point is we say that the antiderivative of lowercase f of x dx is capital F of x, or it's capital A of x plus c as some other general antiderivative. Is everybody okay with that? We're just putting symbols to what we stated in words. Then we're going to evaluate two things. We're going to evaluate one, capital F of B, capital F of B, and we're going to evaluate capital F of A. It's very generic right now. But since we know that capital F of the input is the same thing as uppercase A of the input plus C, then we know that capital F of B is really the capital A of B plus C. And we know that capital F of A is capital A of A plus C. So it's not a coincidence that we chose capital A. That's our area function. Integral from a lowercase a to x f of t dt. So for any area function, here we'll just make a note. Capital A of x is the integral from lowercase a to x of f of t dt. Again, this is not a rigorous thing that you have to follow or remember. We're just kind of loosely showing how we evaluate this thing. So if capital A of x is equal to that in red, then what is capital A of A equal to? What is this right here equal to? Kind of that. So this is capital A evaluated at lowercase a. What if I evaluate this at lowercase a? Then that x becomes lowercase a. What's the integral from a to a?
0.
0. This a, capital A of a, is equal to 0. Okay, well, why did we evaluate those two? Well, we have these two statements here. F of B is A of B plus C, and F of A is C. And then we're going to take F of B minus F of A. So F of B, we have A of B plus C minus F of A, capital F of A, we said was just C. So f of b minus f of a is a of b plus c minus c, which is equal to a of b. And then writing a of b out by its definition, a of b is just the area function evaluated at b. So here's what we're looking at. F of b minus capital F of b minus capital F of a is the integral from a to b on f of t dt. But what was capital F?
The derivative?
Here, let's go back up. So lowercase f was the function. We just chose a random antiderivative as capital F. So capital F was the antiderivative. Where'd that go? Almost in there. So capital F was the antiderivative of f. So we'll say this in words, but what we're looking at is, how do we evaluate the integral from a to b on some function? We evaluate the antiderivative at b, and then subtract off its antiderivative evaluated at a. So that's what we're looking at. What we boxed in there was the fundamental theorem of calculus, part 2. And then part 2 gives us a very short, or kind of a shortcut way to compute this definite integral from a to b. Okay. So that you don't really have to remember that. I just sort of wanted to justify this a little bit. Okay, remember, it says here capital F is any antiderivative of lowercase f. And what this theorem says, to evaluate the definite integral remember, the definite integral is the net area. So to find the net area, or to evaluate the definite integral, we first find an antiderivative of lowercase f then evaluate the antiderivative at b and a. Then we just subtract the results. So that's all we need to do to find the net area for any function. Find its antiderivative, plug in the upper limit, minus plug in the lower limit. Are there any questions on that? So I think we're going to skip to the second part of the fundamental theorem, summarized here again. Before we actually evaluate some of these, the common notation is listed here. For capital F of B minus F of A, it's common to just write the F of X with the bar from B to A to mean this right here. So this thing and this thing are the exact same notation. In other words, here with x over x plus 1, that's our antiderivative, and we're going to evaluate it from 1 to 2 in the sense that we plug in 2 to the antiderivative first. So we have 2 over 2 plus 1, and then when we plug in this lower limit, we're going to subtract that result. So minus 1 over 1 plus 1. Or if we had the ln of x with the bar from 1 to 5, that means the ln of 5 minus the ln of 1. So that's just the notation that's used here. Let's see. If you remember this example number 1, the integral from 0 to 2 of x squared minus 1 dx, that was one of the examples we did in 5.2 using the definition. So you might have forgot, but we did actually do that example, and we did get that result to be 2/3. So I don't know if you remember that or not, but anyhow. So now, in order to evaluate this, we don't have to use unless it tells us to explicitly, we don't have to take the limit of the sum of f of x star times delta x. What we can do is say find an antiderivative of x squared minus 1. So that's the first thing we're going to think about. What's the antiderivative of x squared minus 1?
X cubed over 3 minus x.
Yeah. Power rule, we have x cubed over 3, antiderivative of x squared, minus the antiderivative of 1, which is x. So that's our capital F of x. That is our antiderivative. Notice we're not adding a plus c because the previous page shows us that when we subtract those things, the c's cancel out. So when you find a definite integral, it's always most convenient to choose your constant to be 0. Either way, no matter what your constant is, it will always subtract out. So it says find the antiderivative and then evaluate your antiderivative at the upper limit minus the antiderivative, the lower limit. Okay, so the first one we're plugging into that function is 2. So we're going to have 2 cubed over 3 minus 2. That's capital F of B. And then we're going to subtract off that function evaluated at 1.
0.
Huh? Oh, it's 0, yeah. I don't know why I made that 1. 0 cubed over 3 minus 0. And that's our capital F of A. So capital F of A, that's just 0 in this example. We've got 8/3 minus 2, and 8/3 minus 2 is 2/3. Eight thirds minus 6/3 is 2/3. So it's, the same result, just a whole lot less work. Just like when we looked at derivative formulas. Y'all have questions on that? Okay, how about the integral from 1 to 5, 1 minus x, dx? else get negative 8 yet? Or something different?
Positive 8.
Positive 8? So we find the antiderivative first. What's the antiderivative of 1 minus x?
X minus x squared over 2.
Right. Antiderivative of 1 is x. Antiderivative of x is x squared over 2. And we're evaluating from 1 to 5. So that, at this point in 5.3, if you don't remember your antiderivatives, you've got to go back and review those. So we plug in 5 first. So we have 5 minus 25 over 2. Minus, now we're plugging in 1. 1 minus 1 squared over 2. So again, that's our f of b minus our capital F of A. Or we could say, I guess, capital F of 5. Whoa. So we have, let's call 5 10 over 2 minus 25 over 2 minus the quantity 1 minus a half. 1 minus a half is a half, so minus 1/2. We have 10 minus 25 minus 15 minus 1 is minus 16 over 2, which is minus 8. So the net area is negative 8, meaning if we looked at that figure, there's more area underneath the x-axis than there is above the x-axis. Questions on that? Okay, last one, then we'll stop. What's the antiderivative of 3 sine x?
3 cosine x.
Close.
Negative 3 cosine x.
Right, we'll call that 3 times the antiderivative of sine. The antiderivative of sine. What function do we take the derivative of to get sine? Antiderivative of sine is negative cosine. So keep in mind that the bounds here in terms of the variable dx, they're in terms of the variable x. So this is from x equals to 0, x equals to 2 pi. The negative 3 doesn't really matter. It's just multiplied by the cosine. So, if you wanted to, we could look at this as negative 3 times cosine x evaluated from 0 to 2 pi. And then just multiply the result by negative 3. Oops. So we have negative 3 cosine evaluated at 2 pi. What's the cosine of 2 pi? Just 1. Minus the cosine evaluated at 0. Cosine of 0 is also 1. So this is 0. Oops, sorry, cosine of 0. So I've got this graph here because that's 3 sine x from 0 to 2 pi. And if you notice, when we find this area, we have all of this area above and the exact same amount of area below. So we have this positive area and this negative area, and it gives us a net area of 0. Just so we can kind of visually reconcile that. Do you want to have any questions? So really, the stuff from 5.3, there was a lot. Really, we want to start focusing on here, this kind of thing that we're doing now, not the previous stuff with the area function and all those derivations. None of that will be on the exam. It might show up in the homework and stuff, but for the exam, we're going to start to focus on these kinds of things. So now's a good time to go review antiderivatives, because you definitely need them here. All right, I'm going to pass out